Here is a combined summary of pages 58. The authors introduce the backward differentiation formula, BDF, of order k, denoted as BDFk, for time discretization, which is a theta underscore k, stable. The fully discrete finite element method, FEM, with BDFk timestepping method seeks to find a solution satisfying a specific equation. A weak maximum principle is proven, stating that the maximum norm of the discrete solution is bounded by the maximum norm of the initial and boundary data. The authors define function spaces, including Sobolev spaces and their dual spaces, and introduce the Bachner norm and notation for finite element spaces and their restrictions to subdomains. They discuss properties of the finite element spaces, including quasi-uniformity, inverse inequality, and local approximation and superapproximation properties, which are used to establish error estimates for the finite element method. The operator I_h is defined to approximate functions in h_0 to the power of 1 omega by functions in S_h, and estimates for the approximation error of I_h are established. These estimates are used to establish error estimates for the fully discrete FEM. The authors derive local and global estimates for the interpolation and Ritz projection operators, including the local estimate, 3.5, and the global estimates, 3.6, and 3.7. They introduce the concept of Green's functions, which are used to analyze the parabolic equation, and define the discrete delta function delta h, x, showing that it decays exponentially away from x. The Green's function g, t, x, y, is symmetric and has an analytic extension to the right half-plane, satisfying the Gaussian estimate, 3.12. The authors also derive the pointwise estimate for the time derivatives of the Green's function, 3.14. The regularized Green's function gamma is defined, and its finite element approximation is introduced. The authors establish two parts of the weak maximum principle of semi-discrete FEM, using the pointwise stability of the semigroup and the technique based on the dyadic decomposition and local energy estimates. The authors introduce several sets and notations to facilitate the analysis of the Green's function and its regularized version. These sets, including $q_j, x_0, $omega_j, x_0, and $d_j, x_0, are defined in terms of the distance from a fixed point $x_0 and the time variable $t. The authors also define norms and seminorms, such as the $L² norm, $h⁻1 norm, and $L⁻INFTY norm, used to measure the regularity of functions. Three technical lemmas are presented, providing estimates for the Green's function and its regularized version. These lemmas establish estimates for the $L⁻INFTY norm and $L² norm of the Green's function and its regularized version, as well as the $L⁻1 norm and $L² norm of the regularized Green's function and its time derivative. The continuity of the operator $delta_h⁻1 is also established, with an estimate for the $L⁻1 norm of the gradient of the difference between the regularized Green's function and the Green's function. A parameter $alpha is introduced, which depends on the dimension $d and the convexity of the domain omega. This parameter quantifies the regularity of the Green's function and its regularized version, with a value slightly larger than 1 in the case of a convex domain. The estimates established in these lemmas are used to analyze the regularity of the Green's function and its regularized version, and to derive bounds for the error between the numerical solution and the exact solution. The authors note that the constants in these estimates are independent of the mesh size $h and the point $x_0. The proof of the stability of the constant k is outlined, leveraging the consistency and stability parts of the proof in 21, lemma 4.4. By multiplying $h⁻1/2 in the front, the lowest powers of $h in the consistency part are $h⁻alpha and $h⁻1 plus alpha 2 ensuring the stability of k. The stability part is also examined, revealing additional positive powers of $h that guarantee the stability of k. The problem is then reduced by simplifying the notation and relaxing the dependence of the Green's functions on $x_0. The finite element solution $U_H$ is introduced, and by substituting $V_H equals gamma_H, street, and integrating the result for $t in 0 s an expression for $U_H s x_0 is derived. This expression is further manipulated by introducing $W_H in L squared 0 t tilde s underscore h and choosing $W_H equals tilde u tilde g underscore h ultimately yielding an expression for $U_H s x_0 in terms of tilde g underscore h and gamma_h street $. The solution tilde u of the PDE problem is introduced, and by testing the first equation of 4.15 by gamma street and integrating the result for $t in 0 s an expression for tilde u s c dot tilde delta $x_0 is obtained. By subtracting this expression from 4.14, an expression for $U_H s x_0 is derived, which is then bounded using the maximum principle of parabolic PDEs. The estimate 4.21 is then introduced, and its proof is outlined in section 4.4. The local energy error estimate for finite element solutions of parabolic equations is leveraged, and the expression for $T phi h q_j plus d1j phi h 1 q_j is derived. This expression is then used to bound the term $h1/2 nabla f L1 d_shish ultimately yielding the desired estimate 4.21. The proof of theorem 2.1 is then completed by substituting the estimate 4.21 into 4.20, yielding the desired result. The estimate 4.21 is then proved in section 4.4, leveraging the local energy error estimate for finite element solutions of parabolic equations. Here is a combined summary of the 4 pages. The authors conduct a rigorous analysis of error estimates for the numerical solution of a parabolic equation using a finite element method. They first consider the case where t is in the interval 0, 1, and derive estimates for the solution and its derivatives using the basic energy estimate. These estimates are then used to bound the L1 norm of the solution and its derivatives. The notation K is introduced, representing the sum of several terms involving the solution and its derivatives, and is estimated using lemma 4.4. The authors then derive an upper bound for the L1 norm of the solution and its derivatives by substituting technical estimates into the expression for K. The analysis presented is highly technical, relying on advanced mathematical tools, including the finite element method, interpolation error estimates, and the theory of parabolic equations. The authors then analyze the error estimation for the semi-discrete finite element method applied to a parabolic problem. They introduce notation and assumptions, define the semi-discrete finite element approximation, and its error. The error in the L2 norm of the domain is estimated using a combination of techniques, including the energy method and the duality argument. The bound is expressed in terms of the mesh size, the time step, and the regularity of the solution. The authors also discuss the choice of the time step and the mesh size to achieve optimal convergence rates, showing that if the time step is chosen to be proportional to the square of the mesh size, then the error in the L2 norm of the domain converges at a rate of h squared, where h is the mesh size. Similar analyses are conducted for the error estimation in the H1 norm and the L-infinity norm of the domain, with the authors obtaining upper bounds for the error in each case. The solution to equation 4.48 is expressed in terms of the semi-group at increment h, yielding equation 4.50. Applying the operator minus increment h, 1/2 to both sides, equation 4.51 is obtained, leading to the derivation of estimate 4.52, which bounds the L2 norm of nabla RH eta, T, in terms of the L2 norms of nabla, pH minus RH, and minus increment H, minus 1, gamma HS minus pH gamma, S. This result is established using the exponential decay estimate, 4.53, and the smoothing estimates for the analytic semigroup at increment H. The proof of theorem 2.1 is completed by integrating the inequality, 4.52, for T element of 1 plus infinity, and using Fubini's theorem and equations, 3.6, 3.7, resulting in estimate, 4.54, which bounds the L1, 1, plus infinity, L2, norm of nabla RH eta. By applying the triangle inequality, Holder's inequality, and lemma 4.3, estimate, 4.55, is derived, bounding the L1, 1, plus infinity, W1, 1, dH, norm of gamma H minus gamma. The weak maximum principle of the fully discrete FEM is proved by decomposing the solution into three parts, UNH, 1, UNH, 2, and UNH, 3, which are finite element solutions of problems 5.3, 5.4, and 5.5, respectively. The goal is to establish estimate 5.1, which bounds the L infinity, omega, norm of UNH in terms of the L infinity, omega, norms of UNH, 1, UNH, 2, and UNH, 3. This work presents a novel elliptic finite element method for solving a class of elliptic problems, utilizing the Kronecker symbol and elliptic finite element problems to estimate various quantities. The authors proved three estimates for the elliptic finite element problem, which are crucial for establishing the desired result in Theorem 2.2. These estimates involve the L infinity norm of the solution and its derivatives, as well as the L infinity norm of the boundary data. Here is a combined summary of the 4 pages. The paper employs generating functions to analyze the BDFK method for solving parabolic equations. The authors introduce the discrete elliptic equation of the generating function U, 2, zeta, and its solution map MH, zeta, providing lemmas that estimate the inclusion of dt, E minus tau z, and the behavior of 1 minus E minus tau z, tau. These lemmas are crucial for the analysis of the BDFK method. The authors defined truncated sectors saint and saint, sigma, used to construct contours of integration, and fix an angle theta satisfying certain conditions. Applying Cauchy's integral formula, they derive an expression for UNH, 2 involving the generating function U, 2, zeta, and the solution map MH, zeta. The contour of integration is deformed to GT theta, sigma, comprising GT, 1 theta, sigma and GT, 2 theta, sigma, leveraging the analyticity of the integrand and the periodicity in IM, z, with period 2 pi, tau. This deformation enables the expression of UNH, 2 as an integral over GT theta, sigma, involving U, 2, E minus tau z, and MH, E minus tau z. The authors analyze a semi-discrete finite element method, FEM, for a time-dependent problem, introducing a globally continuous piecewise smooth solution, 2, and decomposing it into 21 and 22. They apply the Laplace transform to rewrite the semi-discrete FEM in terms of the transformed solution, U2, and derive an equation for this transformed solution. A formula for the Laplace transform of a piecewise linear function, GH, is derived and estimated, providing essential bounds for the subsequent analysis. The semi-discrete FEM is rewritten in terms of an operator equation involving the solution map of the homogeneous part of the equation, LH, and an operator difference, MH-LH. The authors bound the operator difference using the properties of theta and a previous lemma, which is critical for their error analysis. These pages provide a comprehensive treatment of the mathematical techniques involved, laying the groundwork for further error analysis in the paper. The paper discusses the analysis of a semi-discrete finite element method for a class of parabolic equations with non-homogeneous Newman boundary conditions. It focuses on the error estimates in the L infinity, omega, norm for the spatially discrete solutions. The authors start by introducing the problem and its semi-discrete formulation, followed by the main results. They then provide the proof of the main theorem, which involves several lemmas and inequalities. The first part of the proof involves bounding the L infinity, omega, norm of the discrete solution A2, T, using the L infinity, partial differential omega, norm of the discrete solution A2, S, and the discrete initial data GH. This is achieved through a series of inequalities involving integrals over certain contours in the complex plane. The second part of the proof involves bounding the L infinity, omega, norm of the discrete solution A2, Tn-1, using the L infinity, partial differential omega, norm of the discrete solution A2, S, and the discrete initial data GH. This also involves a series of inequalities involving integrals over certain contours in the complex plane. Finally, the authors prove the error estimate in the L infinity, omega, norm for the spatially discrete solutions by combining the previous results and using the triangle inequality and theorem 2.1. In addition, the paper discusses the proof of another error estimate for the spatially discrete solutions, which involves solving for UK element of Shay at the time tk and using the triangle inequality and theorem 2.1 to obtain the desired bound. The paper provides a detailed analysis of the error estimates for the semi-discrete finite element method applied to a class of parabolic equations with non-homogeneous Newman boundary conditions. The authors establish the weak maximum principle for semi-discrete and fully discrete finite element methods with k-step BDF timestepping, where k equals 1, 6, using generating polynomials and the discrete inverse Laplace transform. The analysis requires a uniform time step size, and the elliptic equation for the generating function is derived, with its solution represented using Cauchy's integral formula. The L infinity norm of the solution is estimated, applying the resolvent estimate and the L infinity stability of pH, to prove the weak maximum principle. The authors also discuss limitations, noting that their approach cannot be extended to k-step BDF methods or single-step methods with variable time step sizes. However, they suggest that discrete semigroup estimates can be applied to the discontinuous Galerkin (DG) timestepping method with variable step sizes, yielding a weak maximum principle with an additional logarithmic factor. The appendix provides a proof for the weak maximum principle of DG, 0, with variable step sizes using discrete semigroup estimates. The discrete Galerkin method, DG, 0, is then applied to parabolic equations, and the authors establish the weak maximum principle for the DG, 0, method. A discrete harmonic extension and its difference with the discrete solution are defined, and discrete integration by parts and properties of a rational function are used to obtain an estimate for the discrete solution. This estimate is simplified using the properties of the rational function and elliptic theory, arriving at the desired bound. The weak maximum principle is crucial for understanding the behavior of the discrete solution and its relation to the continuous problem. It provides a way to control the discrete solution in terms of the boundary data, essential for error analysis and convergence studies. The results contribute to the development of more efficient and accurate numerical methods for solving parabolic equations, particularly those with non-zero right-hand sides. The paper concludes the proof of the discrete maximum principle for finite element solutions of parabolic equations, demonstrating the stability and analyticity of the numerical method. By combining the triangle inequality with the assumption of a minimum time step size, an estimate of the error in the L infinity norm is obtained, revealing an optimal convergence rate in terms of the logarithm of the time step size and the mesh size. The authors draw on a comprehensive range of references from the existing literature on finite element methods for parabolic equations, including works on discrete maximal regularity, stability, and analyticity. These citations highlight the contributions of various researchers to the field, such as the development of discrete maximal regularity theory, the analysis of finite element methods for parabolic equations, and the study of stability and convergence properties. The paper also engages with the broader scientific community through additional references on finite element methods for elliptic and parabolic equations, as well as papers on numerical methods for ordinary differential equations. Throughout the paper, precise mathematical language and notation are employed, ensuring that the results are presented in a clear and rigorous manner accessible to experts in the field.